So you've already learned about differentiation in Chapter 3, but we're here to talk to you about antidifferentiation, which is Chapter 4. You will now know what the squiggly sign is all about. Let's review. If you were asked to find a function f whose derivative is f of x equals 3x squared, you would probably say that f of x equals x cubed because d over dx of x cubed equals 3x squared. Well, the function f is an antiderivative of f. To define this, a function f is an antiderivative of f on an interval, say I, if f prime of x equals f of x for all x within I. This is the most important part. Now let's talk about the plus c for a second. F is only one of the antiderivatives of f. It is not the antiderivative of f. Take, for example, these three functions. f1 of x equals x cubed, f2 of x equals x cubed minus 5, and f3 of x equals x cubed plus 97. All three of these functions are antiderivatives of f, despite the minus 5 and the plus 97, because these are constants, which we will denote as c. So great. Now that we kind of understand what an antiderivative is, we're going to go over some basic rules. The two most basic rules are the integral of f prime of x dx equals f of x plus c. And, second, the derivative of an integral of f of x equals that f of x. Now let's go over some integration formulas you should memorize, the first one being the power rule. The integral of x to the nth power dx equals 1 over n plus 1 times x to the n plus 1 power plus c, when n is not equal to negative 1. Now let's go over the trigonometric integration formulas. The integral of cosine x dx equals sine x plus c. The integral of sine x dx equals negative cosine x plus c. The integral of secant squared x dx equals tangent x plus c. The integral of secant x tangent x dx equals secant x plus c. The integral of cosecant squared x dx equals negative cotangent x plus c. And finally, the integral of cosecant x cotangent x dx equals negative cosecant x plus c. Notice that in every single one of these integration formulas, we add a plus c. You should never forget this constant. Moreover, you need to memorize these basic integration rules. Now that we know these basic integration rules, let's put them to practice. Given the integral of 3x dx. First, factor out the constant 3, so all you have is x dx to work with. Then, rewrite this so that you can easily recognize that you will use the power rule. Then, use the power rule. Here we get 3 times x squared over 2 plus c. Never forget c. Simplify down using basic math and you have found your answer. So now that we've done an example involving the power rule, let's do one involving trig. Take example 2, the integral of sine x over cosine squared x dx. First, rewrite this integral by separating the fractions, so we have 1 over cosine x times sine x over cosine x dx. Using our knowledge of basic trig identities, we know that 1 over cosine x can be rewritten as secant x. And we know that sine x over cosine x can be rewritten as tangent x. So now given the integral of secant x tangent x dx, this is an easily recognizable trig integration formula we know is secant x. Add c and you have your answer. Let's now transition into finding the particular solution involving c. The integral of f of x dx equals f of x plus c. We know this. This is known as the indefinite integral, which we have just learned. So now we are going to figure out how to find c, because c does equal a number or x. And once you find c, you have now found your definite integral. So how do we do this? Well, let's find c together. Take example 3. We are to find the general solution of f prime of x equals 1 over x squared when x is greater than 0, given the particular solution f of 1 equals 0. Well, first let's find our indefinite integral using the power rule as shown here. We know, based off the power rule, that the integral of 1 over x squared is x to the negative 1 power over negative 1 plus c. So given our particular solution, f of 1 equals 0, we can plug that into our indefinite integral to solve for c using basic math. Now that we have found c, we plug that back into our indefinite integral, and we have found our answer. We all know physics and calculus go hand in hand, so let's put that into practice with example 4. A ball is thrown upward with an initial velocity of 64 meters per second from an initial height of 80 meters. We must find the position function giving the height s as a function of the time t, and we must find when the ball hits the ground. We know from differentiation that the derivative of the position function is the velocity, and the second derivative of the position function is the acceleration. So let's use that knowledge here and plug in the information that we are given. This is why pencil is very important. So through integration, we can find s prime of t. So given our newly found s prime of t function, or our velocity function, we can now integrate that to find our position function. But first, we must find our c. Given the information that the initial velocity is 64 meters per second, we can use that as our c. And now we can integrate to find our position function. So now we have found our position function for all values of t, but we must find the position function when s of 0 equals 80 meters. So using that information, we can solve for c, and once found c, plug that back into our general solution to find our particular solution. We have answered the first part of our problem, but now we must find when the ball hits the ground by setting the position function equal to 0. Solve using the quadratic equation. And we're done. Let's move on. Remember learning that the derivative is the slope of the tangent line of a curve or a function? We'll show that here. Well, the integral is the total area under the curve, as shown here, if the function is positive. Now let's put this into perspective with example 5. We are given a function f of x equals negative x squared plus 5, bounded by the x-axis and the vertical tangent lines x equals 0 and x equals 2. We are going to show you 3 different methods to estimate the area under the curve, using an underestimate, an overestimate, and the most accurate estimate. First, we are going to start with the underestimate, or the lower Riemann sum. Because this is an underestimate, we must draw rectangles under the curve. We can label them 1, 2, 3, and 4. The areas of each of these 4 rectangles added together will equal the total area under the curve. We know that the area of a rectangle is base times height, so let's plug in those numbers here. Notice that all of the heights are the same, or 1/2, so you can factor that out to make solving easier. Solve, and we find the lower Riemann sum to be 6.25 units squared. This is an underestimate of the area. So now we have found the underestimate of the area under the curve using the lower Riemann sum to be 6.25 units squared. So now let's use the upper Riemann sum to find the overestimate. We are going to need to draw our rectangles above the curve in order to do this. The formula remains the same. We can again factor out the 1/2 for all of the rectangles share the same height. Plug in the bases and then solve. We find the overestimated area using the upper Riemann sum to be 8.25 units squared. So now we know that the actual area under the curve is somewhere between 6.25 and 8.25 units squared. So now we are going to look at the most accurate approximation using the midpoint approximation. We must split each of our 4 rectangles in half in order to do this.
We will find new bases through doing this. But again, we can factor out the 1/2 for all of the heights remain the same. We must plug in our new bases and solve. We find the area to be 7.38 units squared. This number represents a more accurately estimated area under the curve. We can prove this by plugging it into a calculator and finding the actual area to be 7.33 units squared. So, to summarize, we have just showed you 3 different types of approximations to estimate the area under the curve. The lower Riemann sum, an underestimate, the upper Riemann sum, an overestimate, and the midpoint sum, the most accurate approximation. Now let's combine finding the area under the curve with indefinite integration to find the area under the curve using definite integration. Here are some properties of definite integrals. If f of a exists, then the integral from a to a of f of x dx equals 0. If f is integrable on an interval a, b, then the integral from b to a f of x dx equals the negative integral from a to b of f of x dx. If f is integrable on the interval a to b, then the integral from a to b f of x dx equals the integral from a to c f of x dx plus the integral from c to b f of x dx. If f is integrable on the interval a, b, and k is a constant, then the integral from a to b of k times f of x dx equals k times the integral from a to b of f of x dx. If f and g are integrable on the interval a, b, then the integral from a to b of f of x plus or minus g of x dx equals the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Let's use these properties to solve the following questions. Take example 6. Given the integral from 2 to 6 of f of x dx equals 10, and the integral from 2 to 6 of g of x dx equals -2, find the integral from 2 to 6 of f of x plus g of x dx. We know using properties that we can separate these two and easily solve to find 8 once we plug in the numbers given. Let's move on to another one, example 7. Given the same integrals, the integral from 2 to 6 of 2gx dx equals 2 times the integral from 2 to 6 of g of x dx. We know from properties. We can plug in our numbers and solve easily to get -4. An important note to remember is that areas cannot be negative, but integrals can. Now we are going to go over one of the most important theorems of calculus, the fundamental theorem of calculus. This theorem states that the integral from a to b of a particular function f of x equals the integral of that function from a to b. The brackets denote the substitution of those limits. You subtract the lower from the upper. Remember, you do not need c. Take example 8. Given the integral from 0 to 4 of x squared plus 2 dx, integrate the function indefinitely without c, including the limits within brackets to denote the substitution of the limits. Plug in the upper limit and the lower limit, subtracting the lower limit from the upper. Use simple math, and we solve to find the answer to be 88/3. This is the area under the curve x squared plus 2. Let's use some trig with example 9. We are to find the integral from 0 to pi of cosine x. We integrate indefinitely to find sine x. Plug in the upper limit and the lower limit, subtracting the lower from the upper, and then solve. We find 0. Now we are going to go over the mean value theorem for integrals. There is one for derivatives, and there is one for integrals. This theorem states that f of c equals 1 over b minus a times the integral from a to b of f of x. F of c represents the average value of the function. Let's take for example 10. We must find the value of c guaranteed by the mean value theorem for integrals If f of x equals 9 over x cubed on the interval 1, 3, we must know that this function is continuous on this interval. So using the mean value theorem, we can solve this problem. So first we plug in what we know. And now, using basic properties, we can factor out the 9 for it as a constant and rewrite the integral so that we can use the power rule. Once integrated, we can use the fundamental theorem of calculus number 1. We plug in the upper limit and the lower limit, subtracting the lower limit from the upper, and solve. We find 4. So we find our integral to equal 4. And using the mean value theorem, we can say that f of c equals 1 over 3 minus 1 times 4. We find that our f of c equals 2. Now that we know our f of c, we can set that equal to our function, replacing x with c, solving for c. We find it to be approximately 1.65. Now we are going to look at the average value of a function on an interval. If f is integrable on AB, then the average value of f on AB is 1 over b minus a times the integral from a to b of f of x. Let's take, for example, 11. We must find the average value of the function, as well as the values of x in the interval 0 to 2, given the function x cubed. So, we can use the average value of a function to solve this problem. We plug in the limits in the function that was given and integrate indefinitely. Now we can use the fundamental theorem of calculus number 1 and find 2 to be the average value of the function. To find the values of x, we set that 2 equals to the function and get approximately 1.26. Now we're going to look at one last theorem, the second fundamental theorem of calculus. This theorem states that the derivative of an integral from a to x of a function f of t dt equals f of x. Let's take example 12. We are given f of x equals the integral from 1 to x of t squared over t squared plus 1 dt, and we must find the derivative of f of x. Well, we can use the fundamental theorem of calculus number 2 and substitute x for t, and we're done. Let's take another example 13. We are asked to find the derivative from 0 to sine x of root t dt. Now, the upper limit is not just merely x, but sine x, so we must denote that u. We remember from derivatives that the chain rule is f prime of x equals f of u times u prime. We know f of u is root sine x, and the u prime is cosine x, and here we have found our answer. Many people confuse when to use the first and second fundamental theorem of calculus, so we're here to clarify. If it's asking for the derivative, you use the second fundamental theorem of calculus. If it is not, you use the first. Don't forget.
Okay, so another way to find the area under the curve we need to touch on is known as the trapezoidal rule. This formula is the difference between the limits over 2 times the number of trapezoids times the bases of each of those trapezoids added together. Notice, you only multiply 2 by the middle bases, for those are the only trapezoids that share 2 sides. Let's look at example 14 together. So, suppose we know the speed of a car every 5 seconds for a 30-second interval given by the table below. Using the data, estimate the distance traveled during 30 seconds. We will draw a table to help gather our information and visualize the trapezoids that we will be using easier. Once we have gathered all our information, we know that we are going to be using the trapezoidal rule, so we can copy it down here. And now we can plug in the numbers that we have in order to solve this problem. First, we subtract the limits, 30 minus 0, and we put that over 2 times the number of trapezoids, in this case 6. Once simplifying that down to 5 halves, we can then multiply by the bases of the trapezoids. Remember, the first base and the last base will not be multiplied by 2, for they do not share any sides. Once simplified, we get approximately 1,175 feet. Just in case you didn't fully understand that example, here's a visual representation of the trapezoidal rule. You basically are taking the area of each trapezoid under the curve using the trapezoidal rule, providing a pretty accurate value of the area under the curve. A special note, you only use this when all of the heights of each trapezoid are the same. If not, then you can just use the Riemann sums. So we've gone over pretty much everything when it comes to antidifferentiation, but there is one last thing we must go over, which is U substitution. U substitution comes in handy when we must integrate composite functions. If f of x is an antiderivative of f of x, then the integral of f of g of x times g prime of x dx equals f of g of x plus c, where g of x is your inside function and g prime of x is your derivative of your inside function. We denote this as u and du. Let's take, for example, 15, the integral of 2 cosine of 2x dx. We must first identify our u and our du. In this case, our u 2x and our du 2dx. As rewritten here, we can identify that we already have our u and our du within our integral. And therefore, we can just replace our 2x and our 2dx with our u and our du. Now we just integrate normally in terms of u, making sure we replace u at the end, and add c, and we're done. Now, let's look at an example that's a bit more complicated. Let's integrate 4 secant squared of x over 2 dx. We can recognize that x over 2 is our inside function, so that's our u, and our du is the derivative of that, which is 1/2 dx. Now, we already have our u within our function. However, we don't necessarily have our du because we have 4 dx, not 1/2 dx. So in order to get that 1/2, we must multiply 4 by 1/8 on both sides. Once we've simplified it down a little bit, we can replace our x over 2 and our 1/2 dx with our u and du and integrate in terms of u. Once we have done that, we can replace our u once more, add c, and we have found our answer. Other times, the variable will be unneeded, not just a simple number like 4 you can manipulate, and this is where it may get tricky. Let's take for example 17 and integrate x times the square root of 2x minus 1. We can easily identify that 2x minus 1 is our inside function and therefore our u, and our du is the derivative of that, or 2 dx. However, what about that x? We don't need it, so how do we get rid of it? Well, just as we have put our 2x minus 1 in terms of u, we must do the same for our x. So we know that u equals 2x minus 1, so let's solve for x, finding x to be u plus 1 over 2. Once we have our x, we can replace that back into our integral and simplify, factoring out our constant, or 1/2, to make solving easier. Now we distribute our root u to make integrating easier. Once we have done that, we must notice that we don't have 2 dx, so we must multiply by 2 on both sides in order to get our du. Once we have our du, we can replace our 2 dx with our du and integrate normally in terms of u using the power rule. And once we have done that, we just replace our u with our 2x minus 1, add a c, and we have our answer. So now we've done a few examples involving indefinite integration, so let's do one involving definite integration. Take for example 18. We are going to integrate the square root of 2x minus 1 from 1 to 5. We can easily recognize our inside function to be 2x minus 1, so let's denote that as our u, and our du to be the derivative of that, or 2 dx. Notice that we don't have a 2 dx, but only a dx, so we must multiply by 2 on both sides in order to get our du. Now that we have our du, we can replace our 2x minus 1 and our 2 dx with our u and du and integrate normally using the power rule. However, now we must change our limits because just like every part of our integral, we must put those in terms of u too. So using our u, or 2x minus 1, we know that if x equals 1, then u equals 1, and if x equals 5, then u equals 9. So now all we have to do is use the fundamental theorem of calculus number 1 and solve. We get 26 over 3. It probably feels like we've gone over a lot of curriculum, and the truth is we have. So thank you so much for watching and keeping up with us. We hope you learned a lot about antidifferentiation. And if any math analysis or pre-calculus students claim that calculus is easy, just show them this meme of SpongeBob, because this is exactly what they look like. Again, we really hope you enjoyed our video and appreciate this meme.